Geometry as inherited structure. A common but often unexamined assumption in discussions of spacetime is that curvature is continuously redefined by whatever matter happens to be present at a given moment. Matter moves, distributions change, and geometry is imagined to endlessly update in response, as if spacetime were a soft surface being reshaped anew at every instant. The proposal here is more restrained and more consistent with how geometry behaves in mature physical theories. Spacetime curvature is not endlessly rewritten by its occupants, it inherits structure. Once formed, geometric features persist, propagate, and constrain motion long after the conditions that shaped them have passed. This claim does not rely on any specific origin story for the universe, nor does it argue about what came first, gravity or matter. It focuses instead on how geometry behaves once it exists. In general relativity, spacetime is described by a metric field that evolves according to well-defined equations. These equations allow curvature to exist, move, and persist independently of local matter occupation. Geometry is not recalculated from scratch at each point in time. It carries continuity. It has history. A useful way to think about this is to treat spacetime geometry as a conserved background structure rather than a moment-by-moment reaction surface. Curvature, once established, does not vanish simply because matter moves away. Gravitational waves are the clearest demonstration of this principle. They are disturbances in curvature that propagate through spacetime long after leaving the region that generated them. The wave carries geometric information forward. It is literally curvature in motion, persisting independently of local occupation. This alone shows that geometry can store and transmit structural features over time. More generally, the field equations of general relativity permit spacetime to retain geometric configurations, even in vacuum. Once curvature exists, it influences future motion regardless of whether matter remains nearby. Trajectories continue to be constrained. Light continues to bend. Free-falling paths remain defined. Geometry doesn't need to be actively refreshed by matter to continue operating. It behaves more like an inherited framework than a reactive surface. This persistence implies a form of geometric memory, not in the sense of information storage like a computer, but in the sense of structural continuity. Early curvature disturbances, whatever their cause, shape the metric in ways that can endure across vast spans of time. Later matter moves within that inherited structure. It may deepen certain regions, smooth others, or locally modify curvature, but it does not erase the underlying framework. Geometry accumulates history rather than resetting. Importantly, this does not mean geometry is rigid or frozen. Spacetime is dynamic. Curvature can evolve, propagate, and interact, but evolution is not erasure. Change happens within continuity. A riverbed can shift over time, but it does not lose all memory of previous flows. In the same way, spacetime geometry evolves while retaining inherited features that continue to guide motion. The independence of curvature from occupation is central here. Regions of spacetime that are sparsely populated or temporarily empty do not lose their geometric character. They remain part of the same continuous structure as dense regions. Motion entering such regions is still constrained by curvature shaped elsewhere and earlier. Geometry does not depend on constant occupation to remain meaningful. By treating spacetime as an inherited geometric structure, the causal narrative becomes simpler and more stable. Matter does not need to continuously instruct spacetime on how to behave. Geometry already knows its constraints. Matter arrives, moves, accumulates, and evolves within a framework that carries the imprint of past curvature. This framing avoids speculative claims while aligning cleanly with how geometric fields behave in established physics. This section stands apart because it clarifies a subtle but critical point. If geometry were endlessly redefined only by present matter, long-range coherence and persistent structure would be difficult to explain. If geometry inherits structure and carries it forward, coherence becomes natural. Spacetime is not a blank slate rewritten at every moment. It is a continuous terrain shaped by its own history, one that matter enters rather than creates anew. Established physics already treats space-time geometry as a structure with continuity rather than a surface that is continuously redefined by present matter alone. In general relativity, space-time is described by a metric field that evolves according to deterministic equations. These equations do not erase curvature when matter moves away, nor do they require constant local occupation to remain meaningful. Once curvature exists, it persists as part of the space-time solution and continues to constrain motion into the future. This framework, introduced by Albert Einstein, inherently encodes geometric continuity rather than perpetual reset. Gravitational waves provide direct empirical support for inherited geometric structure. These waves are propagating disturbances in space-time curvature itself. After leaving the region that generated them, they travel through vast expanses of near-empty space, carrying geometric information forward in time. The curvature does not collapse or dissipate simply because matter is absent. Instead, it persists, propagates, and interacts with detectors long afterward. Observations by the LIGO scientific collaboration confirm that space-time can retain and transmit curvature independent of ongoing matter occupation. This is geometry behaving as a conserved, evolving structure rather than a transient response. Vacuum solutions to Einstein's field equations further reinforce this point. Space-time can possess non-trivial curvature even when stress energy is locally zero. These solutions are not mathematical curiosities. They are physically meaningful descriptions of regions where geometry continues to guide motion despite the absence of matter. Free-falling trajectories remain well-defined. Light paths remain curved. The geometry does not need to be continuously regenerated by occupants. It exists as part of the space-time configuration itself. Geodesic motion also reflects inherited structure. Once a space-time metric is established, geodesics are fixed by that geometry. Objects entering the region later will follow the same constrained paths regardless of whether the matter that originally influenced the curvature is still present. This shows that geometry carries forward constraints imposed by earlier conditions. Motion today can be governed by curvature shaped in the past, without requiring ongoing causal input from the original sources. From a mathematical perspective, the metric tensor is treated as a field with its own continuity properties. It evolves smoothly unless acted upon by new influences, and even then, changes propagate rather than overwrite. This is standard behavior for fields in physics. There is no mechanism in general relativity that instantaneously resets geometry to a neutral state when matter distributions change. Instead, space-time solutions retain history through their boundary conditions and prior evolution. Crucially, none of this requires claims about how curvature was first generated or what mechanisms dominated early cosmic conditions. The support here is strictly local and structural. Once curvature exists, it behaves as an inherited framework that persists, propagates, and constrains motion independently of current occupation. Matter may modify geometry, but modification does not imply continual redefinition from zero. This is why treating space-time geometry as inherited structure aligns naturally with known physics. Geometry behaves like a conserved background field with memory in the form of continuity, not like a reactive surface that forgets its past. The persistence of curvature across empty regions, the propagation of gravitational waves, and the stability of geodesic constraints all point to the same conclusion. Space-time carries its structure forward. Matter moves within that structure, but it does not need to constantly recreate it.